All right, welcome back to video number 4, I believe, of 3.1. We're still doing the chain rule. We're applying it to different situations. As long as there's a composition, the chain rule can help us find the derivative of something like number 8. So we're saying, can we rewrite this in terms of u, right? In terms of an inner function that we've already identified is this green box. So I'm going to say my function that I have here is really the natural log, ln, of u, because u is the whole green expression. The chain rule says if you want to find the derivative, take the derivative of the outer function. Well, what's the derivative of the natural log? 1 over x. Oh, but I don't have 1 over x. I don't have the natural log of x. I have the natural log of u. So therefore, that's 1 over u times the derivative of the inside function, which would be u prime. And maybe I shouldn't put an equal sign. I realize that we're describing a function in terms of x, but we have things in terms of u. Like, it's a little iffy, but that's okay. All right, so this is what I need to find. I need to find what is 1 over the inside function times the derivative of the inside function. But we already did all the pre-work, right? Our answer is going to be 1 over everything that I see in green, 4x squared minus 5x plus 7, times the derivative of the inside, which we said was 8x minus 5. Make sure to put this in parentheses, please, because if you just dangle it out there without parentheses, again, it looks, if I didn't put the parentheses, it would look like I have the fraction times 8x and then minus 5 later. But no, it's the fraction times 8x minus 5. To remedy that even a little bit more, or to make it clearer, we can say, oh, this is over 1, and then multiply those two fractions and get my final answer to be this. And it turns out that whenever I deal with natural log and I'm finding the derivative of the natural log is the derivative of the inside over the inside. That basically is what it amounts to. The derivative of the inside over the inside, or the derivative, yes. Okay. And we're done. This is the derivative for our original function g of x. We took the derivative. This is what it is. Not too bad, right? As long as you identify the inside, and if you can take the derivative of the inside, take the derivative of the inside, and then we can just put everything in the right spot. Here's an exponential. I have e to the something. So therefore, my function is e to the u, because that's the something. I declared it over here. And the derivative of e to the u is just e to the u. I'm sorry, I should say f prime of x, which is what I'm looking for, is e to the u. I don't know if I did it over here. I did not. Oh, I did. Here, g prime of x is that. So f prime of x is e to the u times the derivative of u, which is u prime. Oh, but I have u, not u. But I have u. It's e to the 2 minus 5x times u prime, which is negative 5. Or I would just write it as negative 5e to the power of 2 minus 5x. And there's our answer. We found the derivative of this more complex function because it's a composition of two different functions, an inner function in green and then the outer function, which is the exponential. And then finally, if I do this one, or actually there was another one, wasn't there? Ooh, this one looked fun. Maybe we should do this one instead. According to what we already did, we said this is the inside function. So therefore, my outside function is 4 divided by the square root of something. That's something I'm calling u. And then we're going to take the derivative of this. But I can't take the derivative of square roots using the power rule unless I rewrite them. So I need you to remember that whenever you have a square root, that's the same thing as a 1/2 power. But even if I did that, I cannot take the derivative in the denominator. So therefore, this I have to rewrite again, or even more, I should say, as u to the negative 1/2. Now I have a power function. I have a coefficient. I have a variable to an exponent that's a numeric exponent. Now I can use the power rule. So I'm ready to take the derivative. Let's see. The derivative is, by the way, every time I wrote a u here, maybe I should have kept it in the original color, which is green. All right, the derivative. The derivative of 4u to the negative 1/2. By the way, all of this line, we just rewrote it, right? We didn't take any derivatives. Whenever you change radicals, square roots, or cube roots into fractional exponents, that's not a derivative. That's just rewriting it. Whenever we rewrite powers that are in the bottom and move them to the numerator with a negative exponent, that's not taking the derivative. That's just rewriting it. Now I'm ready to take the derivative, so I'm going to multiply that times that. That'll give me negative 1. That'll give me negative 2, not negative 1/2. U to the power of negative 3/2. If you subtract 1 from negative 1/2, you get negative 3/2, or negative 1/2. Times, don't forget, we have to multiply by the derivative of the inside, so the derivative of u. If I'm calling u the inside, then the derivative of u would be u prime. Great. Now we can do our substitution back and say, instead of writing u, we can write x squared plus 3. And instead of writing u prime, we can say times 2x. At this point, this is the correct answer. If you're on a free response, this is probably where you have a good stopping point. You don't need to simplify anymore, but on a multiple choice, this is probably not looking like one of the choices. So what do we need to do? I see a negative exponent. We need to flip it over. I also have 2x times negative 2, so that's going to leave me with negative 4x over, and then all of this other stuff will move to the bottom and become positive exponent. So you could leave it like this, or you can say whenever I have an exponent that's a fraction, I can rewrite it as a radical. So this is really the square root of x squared plus 3, and x squared plus 3 has a power of 3. So a fractional exponent means I'm taking the square root because there's a 2 on the bottom, and I'm taking everything else to the third power. And that's what we have, and that is the derivative. I guess we'll do one more video here, and we'll talk about what happens when you do the chain rule with tables of values where you're not given an equation to take the derivative of or differentiate.